In this video, we're going to go ahead and tackle logarithmic functions. So if you're following my lecture series, we have stepped back into a discussion of logarithms. We have just finished a discussion of inverse functions and how to find inverse functions. And that was necessary prior to getting into logarithmic functions, just because, well, we'll see in probably not this lecture, but next lecture. So it's just important to know that you do need that information. Actually, maybe we will tackle it in this lecture. Anyway, the prerequisites here are that you need to know exponentials, just everything about exponential functions, how to graph them, how to evaluate with them, and then also you should know about logarithms, basic stuff like log base b of x is equal to y really is saying the same thing as b to the y is equal to x. That's that circular argument that I've talked about several times. You should also be very familiar with functions and function notation, all that fun stuff. And finally, solving equations. You should be able to solve equations. Actually, I'm going to stick one more thing on here. You should be okay with the idea of inverse functions. And that's just from that last lecture I did. Now, if you are missing any of these topics, please go back through my videos and find the topic that will fill in the gaps. So let's go ahead and jump right into it. The definition of a logarithmic function is a function of the form f of x equals log base b of x. Now, we've actually seen this for quite some time because of the logarithmic discussion we had in a previous lecture, but we were using y equals log base b of x. Obviously, now we're switching y for f of x. Something I want to mention here, this is how textbooks list it out, but honestly, a logarithmic function could be of the form a times log base b of x minus h plus k. In other words, if you think of shifts and translations, which again is something that we talked about in the past when we dealt with functions, you can apply shifts and translations to graphs of logarithms, which we'll again talk about in the future. But the fact is that it doesn't just have to be log base b of x. It could be 3 times log base 7 of x minus 4 plus 10 or something like that. It could be anything like that. So this is a logarithmic function as well. Don't want to fool you into thinking that they're all just these simple looking things. So let's go ahead and use this new function notation. If f of x is equal to log of x, and remember, I'm just trying to sneak in little definitions that we've used in the past, recall that notation, just regular old log of x, is equivalent to saying log base 10 of x. If there's no base given, it's assumed it's base 10. So let's go ahead and evaluate this function at 1. And this works like any other function. Just even if it works like it was a square root function. If this, just imagine log just replaced with a square root symbol. Okay, so we just plug in 1 for x. So log of 1. Now the question really here is, we know that the base is 10. I know it doesn't look like a 10 down there, but it is a 10 down there. I'll maybe make it nicer here. But we know the base is 10. That's a little bit better. So we have to ask ourselves, 10 to what power is equal to 1? Well, I know 10 to the 0th power, right? Using that circular argument, is equal to 1. 10 to the 0th is equal to 1. So f of 1 is just 0. And again, you see the strength of function notation, because when somebody comes up and they don't know maybe what the function we're dealing with is, but if they see this notation here, they say, oh, I see you plugged in 1, you got out 0. So again, just trying to reiterate that function notation has this powerful attachment to it, that we get inputs and outputs kind of put together. In other words, ordered pairs. So let's take a look at f of 7.93. Well, I know that's going to equal log of 7.93, or in other words, log base 10 of 7.93. And I do not know what I have to raise 10 to reach 7.93. A good thing to think about, though, is one that it's log base 10. But the other thing to think about is it'll be 10 to some power, I'll put a little question mark here, is equal to the inside. You can kind of estimate this. I don't recommend it, but you can. Try a value of 0 for that question mark. 10 to the 0th is going to be 1. So, nope, it's not going to be a 0. It's probably going to be bigger than that. So try 10 to the 1st. Well, 10 to the 1st is equal to 10. That's too much. 10 to the 0th was 1. 10 to the 1st is 10. So it's going to be some number. Our input here is going to be some number between 0 and 1. It'll likely be nearer to maybe 0.8, 0.9, something like that. But the only way that you can actually get this value is to use a calculator, scientific or a graphing calculator. So I'll bring up my graphing calculator here. And your calculator should have a button that says LOG on it, whether it's a scientific or a graphing. So just hit that, LOG, and then 7.93. I like to close out parentheses. It's actually not necessary here, but I like to do it. And like I said, it was either 0.8 or 0.9 somewhere in there, and there we are. It's a 0.9 essentially, but let's go ahead and round to the nearest thousandth. So this is roughly equal to, not exactly equal to, 0.899. And finally, let's take a look at f of -1. I know that you're thinking, well, you're just plugging in values, so okay, I get it. You don't have to go any further. But it's good to do this example, actually. This is going to be log, again, base 10 of -1. So we're asking ourselves, 10 to what power is going to equal -1? I guarantee you no such power exists. So none, I guess, is a good way to say it. There's no such power that exists. You could try 10 to the -4th power, but once you start plugging in negative powers, it just becomes 1 over 10 to the 4th, which is still positive. So no matter what you plug in for our exponent there, it's always going to be positive. So this does not exist. It just doesn't exist. And that tells us something, actually, about the inputs for the log. I know that the logarithm can never return, or in other words, I'm sorry, I know that 10 to a power can never return a negative number. That's just, I mean, it makes sense. That's what we're saying here. So let's go back and adjust our definition. So our definition was just of a logarithmic function was f of x equals log base b of x. And now we know the input must be positive. And then we're going to explore, can it be 0 too? So let's go ahead, I'm just going to pop back to this page and ask you, can you think of 10 to a power that is equal to 0? There's no power of 10 that will turn out 0. Again, for the same reason why there's no power of 10 that will turn out a negative number. So I will again adjust this definition just slightly and write in here where x is strictly positive. So this tells me actually, as a side note, that the domain of this logarithmic function is always 0, and it actually will grow on forever. It will go up forever, and we'll discuss why later on. But the domain can't be less than 0. We can't plug in anything less than 0, and we can't plug in 0 itself. So it starts at 0 and then continues to grow. We can plug in any positive value we want. And that's, plugging in any positive value should be kind of obvious, because I can go, let's say, I just make up an example and I say, oh, well, let's see if we know what log of 31008 is, or something like that. That's a large number that we're plugging in. Can it happen that we plug in a large number? Well, let me ask this. Can it happen that I have 10 to some power is equal to a large number? Yeah. I can find a power of 10 that's equal to that, sure. I mean, it won't be a nice, pretty power, but it'll be a positive power of 10. Now I want to draw your attention back to the properties of logarithms that I've mentioned before. And I don't expect these to be memorized, I expect them to be understood. Like, it should be understood that log base b of b to the p power is equal to p. And the reason why you can understand something like that is just ask yourself, b to what power should equal b to the p power? And that's a pretty obvious answer. B to the p power should equal b to the p power. So that's where a level of understanding comes in of logarithms and how they operate. But there's one more that I'm going to tack on here today, and that's this one down below. B raised to the power of the log base b of x is equal to x. This actually requires a proof, because I think that it's just very important for students to understand where this comes from. Because if you're not used to logarithms, this is pretty foreign, this concept. Like, how does that happen? So let's go ahead and do a proof of this. So we want to prove b raised to the log base b of x is equal to x. So let's assume we're given that. And actually, let's not assume we're given that. We can't assume that, because then we were assuming the proof. So instead, let's assume that we're given that log base b of x is equal to some number. Okay? So this is just an important kind of beginning. We don't know what it is equal to. I'm not assuming that it's equal to x. I'm just going to suppose it's equal to some number, y. I'll just call it y. These are just variables. I have no idea what they equal, right? We know one thing. We know that, well, I'm going to use different letters here. We know that c raised to the d power is equal to, let's do t, okay, implies that log base c of t should equal d. Okay, this is just converting between logarithmic form and exponential form, or exponential form to logarithmic. Use a circular argument and you'll have to agree. C raised to the d power is equal to t, and that's exactly what we have here. So we know that this statement is true just from logarithms. From the definition of a logarithm, that must be true. That's what logarithms say is true. So let's go ahead and use that here. We have that b raised to the power of something here, I'm not going to say it out loud, is equal to y. Well then, by what we know, which is this business right here, we know that log base this base right here, so log base b, I'll write that in, of the right hand side here, which is y, write that in, must equal the exponent. Again, this business right here. So let's go ahead and write that in. Log base b of x. Now before I continue on, I'm almost done actually, but before I continue on, I want to make sure that you see that what I've done is exactly what we're saying here. If you do the circular argument, you'll see this is just saying that log base b raised to this power right here, this picture, is going to equal y. Log base b, b raised to, I said log base b raised to the log base b of x should equal y. Just using the circular argument. B raised to the log base b of x, which we have here, is equal to y. Oh yeah, these two are equivalent. Okay. Now that we have log base b of y is equal to log base b of x, well, it's pretty apparent to see that this must imply, since the logarithms base b of y equals the logarithm base b of x, that's got to imply that y must equal x. Or in other words, way back in the beginning, right back here, when I said we're just going to assume that b raised to the log base b of x is equal to something, but we don't know what, we now know what it equals to. It's equal to x. Or in other words, log, or not log, in other words, b, sorry, raised to the log base b of x is equal to, instead of y, I know y is equal to x, so I'm just going to say x. And there we go. That is the proof. Okay? So, we find out that log base b of b to the x power is just x, and b to the log base b of x is equal to x. In other words, the logarithm base b of the exponential function that's base b returns the input, and the exponential function base b raised to the logarithm base b returns the input. That is, the logarithm undid this exponential function, and this exponential function undid the logarithm, as I've written here. What does that mean? Well, if you watch the video on inverse functions, it means that these two must be inverses of each other. So this is a huge observation and a big theorem that logarithms and exponentials are inverses of each other. Let's go ahead and write that down. So here's the theorem. If f of x is equal to b to the x power, then f inverse, the inverse function of f, is log base b of x. And the converse is also true. If f of x equals log base b of x, then the inverse function, f inverse of x, is equal to b raised to the x power. And remember, this notation doesn't mean f raised to the negative 1. It means f inverse. It's not an exponent. Okay? Which implies to us that logarithms and exponential functions are inverses. A simple example to get us kind of in the mood for this. Let's go ahead and let f of x equal log base 2 of x. Just take a simple example. Well, by that last theorem, that implies that the inverse function, f inverse, must equal 2 raised to the x power. It's just, basically we say log base 2, and the base of the corresponding inverse exponential function is 2 as well. So they both have the same base. And a lot of people just rip off the word log and you have 2 raised to the x. That's kind of how I used to think of it as well. By the way, I'm missing an of x here. It's kind of bothersome. Okay, so let's go ahead and evaluate f inverse of f of 8. This is called composition of functions, first of all, which is a topic that I may or may not have talked about already. But if I haven't talked about it, it's pretty simple to kind of gather. You just essentially grab f of 8. You follow the order of operations. So I look inside the innermost parentheses. I see I have an 8. Can you do anything with that? No. Okay. Then I look in the next innermost parentheses and I see an f of 8. Can you evaluate that? Yeah, sure I can, because I know how to evaluate a function. That'll be f inverse of, I'm going to plug 8 into f, so that's log base 2 of 8. And log base 2 of 8, well, you might not know it offhand just because you're so new to logarithms, but you should start getting used to it. The question is, 2 to what power is equal to 8? Well, 2 to the third power is equal to 8. So log base 2 of 8 should be 3. And finally, since there's nothing else I can do inside these inner parentheses, I will now look on the outside of those parentheses and see if there's anything I can do. Well, yeah, sure, I can evaluate f inverse at 3 here. So let's go ahead and do that. F inverse of 3, well, here's f inverse right here. When I plug in 3, I have 2 to the third power, which is 8. Now, realize that our original number we plugged in was 8. So I plugged in the number 8 into the log, evaluated that, plugged that result into the exponential function, evaluated that, and I got back out my original value. They undid each other. Plugged in 8, got out 3, plugged 3 into the inverse, got back out 8. You should probably expect the same behavior here. Again, following the order of operations, look inside, you see, oh, I have a 4, can't do anything with that. So you go outside those parentheses, you have an f inverse of 4, and you can do something with that. So let's go ahead and evaluate that. That is equal to f inverse of 4 is 2 to the fourth power, or in other words, it is 16. Well, now I can hop outside those parentheses and evaluate the function f at 16 itself. So f is log base 2 of, log base 2 of 16. The question is, 2 to what power is equal to 16? Well, it's 2 to the fourth power. So I get this answer of 4. Now let's follow this chain of commands here. I originally plugged in 4 to my inverse function, got some output of 16, plugged that output of 16 into the original function, and it undid all that work and returned 4. There you go. It's a great justification that these are inverse functions. So what power does that give us? Well, not much when you're solving a logarithmic equation. Solving logarithmic equations, I just still always have the habit of rewriting them in exponential form no matter what. So I know using the circular argument, this is just saying 2 to the negative fifth power is equal to x. So 2 to the negative fifth power is equal to x. However, if you don't like the circular argument and you want to use the theorem, one of the theorems that we have, you could apply the inverse function to both sides. Now remember when I had our discussion about inverses and I said, oh, well, you have 3 plus x is equal to 7. You would apply the inverse of adding 3 to both sides. The inverse of adding 3 is subtracting 3 from both sides. So you apply the inverse function to both sides and you get an answer, right? Well, the inverse of a log base 2 is 2 raised to. So to apply the inverse to both sides of this equation, I would say, oh, let's take 2 on both sides and raise it to what these sides are. So I would say 2 raised to the log base 2 of x is equal to 2 raised to the negative 5. And we have a theorem that says 2 raised to the log base 2 of x is just equal to x because they undo each other. So you get the same answer, but honestly, I think it's kind of long-winded when you're solving logarithmic equations. Really, by the way, this is not the final answer. Your final answer should be 1 over 32. Really, the time where I use a lot of the inverse logarithm stuff, or taking advantage of the fact that logarithms and exponentials are inverses, so when I'm solving something like the following: 3 raised to the x power is equal to 17. In this case, I want to undo the exponential function here so I can unlock this exponent. And what undoes an exponential function is a logarithm. So I could take the logarithm of both sides, base whatever I want. Well, technically, actually, I could take the logarithm, base whatever I want. So I could say log base 10 of both sides. I could do that. And that's actually what I tend to do when I teach. I take the log base 10 of both sides and I get this business. Log base 10 of 3 raised to the x power equals log base 10 of 17. The problem, though, is that we haven't been introduced to the idea that this will unlock this exponent even if these bases aren't the same. So I can't really take that approach yet. I'll show you the approach you initially take, and then we'll gradually move on and away from that approach. But the reason why I'm teaching that approach first is because it gets us used to the idea that logarithms and exponentials are inverses. So if I'm going to find what x is, I'm going to take the log base 3 of both sides, right? I want to undo that base of 3 by taking log base 3 of both sides. When I do that, I know that this logarithm base 3 will cancel this exponential function that has base 3, and I'll get x is equal to log base 3 of 17. That would be the answer. There's an issue with this. The fact is I have no way to calculate what this answer is because I don't know what I don't have a log base 3 button on my calculator. And we'll actually remedy this situation in a future lecture when we talk about properties of logarithms. But this is perfectly fine right now. Log base 3 of 17 is a perfect answer. But just know that there are a lot of ways to write this answer, either doing a decimal approximation or writing it log base 10 if you wanted to. But unfortunately right now, for right now, I'd like this answer. So let me just give one more example here so that we kind of get used to it. Example C. If you're solving an exponential function or exponential equation of like, 31 raised to the x plus 3 power is, or maybe minus 10 is equal to 28. I don't know. If I want to solve that, one thing I know is I have an exponential function here. This exponential expression has an unknown in its exponent. So the only way to unlock that is to take the inverse of this function, which would be log base 31. But unfortunately, I have some other things going on in this problem. So I need to add 10 to both sides first. You have to get the logarithm or the exponential by itself first before you take the log of both sides. So we're going to go ahead and solve for the exponential first. I mean to write 8. And that's when you add 10 to both sides, you get 38 here. And now I'm going to go ahead and take the log base 31 of both sides. And we know log base 31 is the inverse of an exponential function of base 31. So those two will undo each other, and I will just have x plus 3 on the left-hand side. And that's equal to log base 31 of 38. I'll subtract 3 from both sides now, and I'll get x is equal to log base 31 of 38, and that is going to lose 3 from it. And that's it. That's the final answer. There's no way you can clean this up. Well, not with the technology that we have right now. Another type of problem is that somebody hands you a function. They say, I want you to solve this. F of x is equal to this number. So in this case, f of x is log of x, and we want to solve f of x is equal to a negative 5.12. All that's basically saying is that this log of x is equal to a negative 5.12. I just want to get you exposure to this. And now I know the base of this is 10, and I'm not going to use inverse notation here. I'm just going to use a circular argument. Rewrite this in an exponential form. Log to that power equals the inside. So in other words, 10 to the negative 5.12 power must equal x. And of course, I can use a calculator to figure out what that is. Now, the number of applications for decimals, or not decimals, but for logarithms is pretty intense, because it turns out that human beings, we react logarithmically. Our senses are pretty much on a logarithmic scale, which I'll describe more as we kind of get into graphing logarithms, but a brief description of it is this. The more that something incurs, the less effect it has. In other words, if you had no food for days, and then somebody gave you a strawberry, that you went from nothing to all of a sudden having something. That's a huge satisfaction for your taste buds, right? But if you kept eating strawberries every minute, okay, while you're continually, getting the same number of inputs, one per minute, after a while it becomes less satisfying for you. It's still satisfying, but it just becomes less spectacular. So, and that's kind of how logarithms work, is that the greater the input, the less effect it begins to have as time goes on. It still increases, but it just has less effect. And that's how we do it. That's how humans operate. Again, I'll talk about that later on. But here's a certain application for decibel levels. The loudness of a sound measured in decibels, which is the abbreviation for that is dB with a capital B, is D equals 10 log of I over 10 to the negative 12th power. Now that's from a textbook that I currently use, and I don't like the form of it. I would rather write this as 10 times log of I times 10 to the 12th power. Honestly, I'd like it that way, just because it makes sense, right? You can rip the negative off that exponent and put that thing upstairs. So that's really what it means. Anyway, where I is the intensity, the energy intensity of the sound waves in watts per square meter. So that's the actual energy, not the sound we hear. I is the energy emitted from the sound. Okay, and then this equation will give us the actual sound level that we hear, and a reference level that we consider to be correct. Now, something to let you know about If you have a different textbook, I have seen 2, 3, or 4 different versions of this. Some involve 2 different variables, whatever. So just to let you know that this is not the only logarithmic equation for decibels. There's other equivalent formulas, but I'm going to use this one for my examples. So using this formula, the loudest sound emitted by any living source is made by the blue whale. Its whistles have been measured at 188 decibels and are detectable 500 miles away. That doesn't mean they're at 188 decibels 500 miles away. It just means that they're detectable 500 miles away. That 188 decibels is usually measured at 1 meter, which you shouldn't want to be 1 meter away from a blue whale, just by the way. Anyway, find the intensity of a blue whale's whistle in watts per square meter. Now remember, the decibel level is equal to 10 times the log of the intensity times 10 to the 12th power. Now, this equation here we need to substitute in some values for. So we were given that the blue whale's whistle loudest that they measured is 188. So let's plug that in. 188 for the decibel level is equal to 10 log of I times 10 to the 12th. Now I want to tell you something about the decibel level here. It is all it's going to return to us is a number that gives us a reference. Okay, normal human conversation is probably around 65 decibels. A whisper is probably 30 decibels, but it doesn't. The number that we're given doesn't really give us an idea of how powerful a conversation is, how much energy is flowing through the air when a sound is made. So this, finding the intensity, will tell us that. Because this number 188, that's not a large number. If you have $188 while you're very happy, it's not a super amount of money. So it doesn't really give us a good indication of the meaning of 188. In fact, $188 could be a lot depending on what time period you live in, right? Or it could be very little. Okay, so anyway, solving this, we'll divide both sides by 10. So I get 18.8 is equal to log of I times 10 to the 12th. And again, I'll use the circular argument here. Remember, the base on this is 10. Circular argument, just to get me out of logarithmic form, says that 10 to that power should equal the inside. Am I a little raised too simple? So let's write that down. 10 to the 18.8 power should be equal to I times 10 to the 12th power. And now I want to divide both sides of this equation by 10 to the 12th. Let's go ahead and do that to find out what I is, what the intensity of the blue whale's whistle is. On the right hand side, 10 to the 12th over 10 to the 12th is 1. So you just get a single little I there. On the left hand side, 10 to the 18.8 over 10 to the 12th, well, you subtract the exponents, right? So that's going to be 10 to the 6.8 power. So the intensity, the power that is generated by the blue whale's whistle, well, that measured whistle that they have, that they're quoting here, is going to be 10 to the 6.8 power. 6.8. Let's see what that comes out to be. A large number, right? 6,309,000. 573 watts per square meter. The question is that a lot or is that a little? Unless you have an intimate understanding of power how power works, this number here, this intensity, makes no real sense to you. It seems like a lot, though. 6 million it seems like a lot. But let's see how powerful that is compared to normal human conversation. That is, how many times more powerful is this than normal human conversation, which I told you a moment ago is roughly around 65 decibels. Now, kind of a word to the wise, a little word of warning here. The decibel level for that blue whale whistle was 188, right? Now, if I said you had 3 times the amount of money that I have, and you have $6, I'd have $2. So in other words, you'd say 6 over 2. If I have 2, you have 3 times that. That's 6. And it's basically a ratio of 6 to 2. And that's how we're going to do this as well. We're going to see how many times does my amount of money go into 6. 3 times, that tells me you have 3 times the amount of money. If you think that this is how this is going to go, it will, but not with these values. You're not going to use the decibel levels because this 65 and this 188 is not the power. It's just our reference number. But it's not the power. The power is the number of watts per square meter. In reality, so this is wrong. In reality, we want a fraction that has the amount of power the whale's whistle is divided by the amount of power that human conversation is. So we'll take the power level of the blue whale's whistle, and we'll see how many times the power level of human conversation goes into that. That'll tell us how many times more powerful the whale whistle is. It's just a word of warning. Don't use a decibel level. That's just a reference level. It's a reference that we use in real life just to say, oh, hey, this is an easy number to quote. Nobody wants to walk around quoting 6.3 million for a decibel level. So, all right. Let's go ahead and reach for the equation, which is d is equal to 10 log of I times 10 to the 12th. I is the intensity, the power level we want to find out for normal human conversation. We happen to know that it's 65 decibels. And I'm going to do the same thing I did for the whale whistle here. I'm just going to solve for I. Divide both sides by 10. I'll get this business. And then do the circular argument, right? This says that 10 raised to the 6.5 power should be equal to the inside. I'll write that down. 10 raised to the 6.5 power should equal the inside. And now I will divide both sides by 10 to the 12th. 10 to the 12th. 10 to the 12th. On the right-hand side, the 10 to the 12ths cancel. They just become 1. So I'll go ahead and put that in there. So the I is equal to. On the left-hand side, you subtract exponents. 6.5 minus 12 is a negative 5.5. So that's 10 to the negative 5.5 power. So the intensity, the power level of normal human conversation, is how much power you generate when you talk, is roughly equal to, well, all I'm going to do is go ahead on my own and plug this into my calculator that's in my hand right now. I get the following, that the intensity is roughly equal to 0.0000, I think I have one more zero in there actually, 0.316, and then there's some repetitive 2's, so I'll just say 2. So that's the amount of power in watts per square meter that you're kind of throwing out there when you talk in a normal conversation. Not a lot of energy, right? Not a lot of watts. It's not creating hardly anything. However, compare that to the blue whale, and you'll see that this is pretty intense. So let's find out the ratio of the blue whale's power outage to our power outage. Power outage is a kind of a weird saying, actually, but if you take this ratio, and I'm just going to take it with these rounded numbers, even though you shouldn't. You should do it with the exact numbers, but this is just a rough estimation. I have 6309573 divided by, let's see, 0.123453162. Wow. Okay, so this is roughly equal to 1.995 times 10 to the 12th. This many times more powerful. So how many times more powerful is that? Well, let's see. I have a 1995. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Almost 2, let's see, that's millions, billions, almost 2 trillion times as powerful. Holy moly. It's super powerful, actually. So there you go. That's enough to do some damage, actually. So that gives you a better understanding of how much. Here, notice the decibel levels were only 65 for human conversation and 188 for the whale whistle. That told you nothing about how many times more powerful this is. So it turns out that it's about 2 trillion times more powerful. That's incredible. By the way, we could have calculated this ratio by using the exact value. So the exact value for the power intensity for the whale was 10 to the 6.8. The exact value for the power intensity of normal human conversation was a negative 5.5, which is going to be 10 to the 6.8 minus a negative 5.5, or in other words, 12.3. And when you plug that into a calculator, 10 to the 12.3 power is going to be, well, about 2 trillion still. So there you go. Another great application for logarithms is again for a human sensation. This is a kinetic sensation, one instead of an audible sensation. And this one is for measuring motion. We use the Richter scale to measure earthquakes. And so the formula for this is m is equal to log of a over a naught, where m is called the Richter number. That's like an earthquake level of 4.8 or 5.6 or 7.1 or something like that. A is the amplitude of the current earthquake that you're trying to measure on the size of, it's an amplitude of the seismographic trace. So it's how far away from the center that the seismograph kind of wiggles. So you see that seismographs do stuff like this. That would be a really strong wiggle, so they'd measure that, right? And then finally, A sub 0, or A naught, is the smallest detectable quake. It's the seismographic wiggle associated with the smallest detectable quake. Okay? So that's the formula that I'm going to use, but like I said, with everything involving logarithms, there's usually more than one equation, and I've seen 2 or 3 different equations for earthquakes using logarithms. So in these styles of problems, I really like to look up real data here. And so these are Richter numbers on the left-hand side for different earthquakes. And the one I'm interested in is the earthquake that occurred in San Francisco in 1906. Had a Richter number of 8. That was the Richter number. So let's go ahead and just mention that right here. I'm going to say the Richter number for the 1906 San Francisco quake is 8.0. By the way, that quake pretty much destroyed like a ton of buildings in San Francisco, and a lot of the damage was just due to the fact that, well, one, the quake itself, but two, they couldn't stop the fires because they didn't have the infrastructure for it, I guess. And we're going to compare the power of that quake to a couple more recent and more known quakes. We'll take a look at the earthquake that caused a tsunami in Indonesia back in 2004, and we'll look at the earthquake, the largest measured earthquake, because there were several, that caused the damage and the horrible stuff that happened in Japan this a couple of years ago, which would be this one right here. So Japan was 9.0, and then the tsunami was a 9.2. And the reason why I'm taking these just because they're popular and people have talked about them quite a bit recently. And I also want to kind of use these to show you how much these numbers really give us very little idea of how powerful a quake is. So let me ask you, how many times more powerful was the tsunami in 2004, the quake that caused the tsunami in 2004, than the quake that caused all that destruction in Japan in 2011? And then in part B, we'll go ahead and ask the same question. How many times more powerful was the Indonesian quake than the San Francisco quake? Each of these caused significant damage and loss of life. Okay, but it's important to kind of get this idea. So each of these we're going to go through and find out what their actual magnitudes were measured to be via the seismographs, and then we're going to compare those magnitudes via the seismograph magnitudes or amplitudes, and to get these answers. So recall that the Richter scale formula is m equals log of a over a naught, where a naught is the smallest measurable quake. Substituting Indonesia's Richter number into that formula, we get the following. And I know it's log base 10 of a over a naught, so I'll do the circular argument here that says that 10 to the 9.2 power is equal to the inside, which means that 10 to the 9.2 power is equal to a over a naught. In this case, I don't know what a naught is, and I'm only trying to find the amplitude of this quake. So let me just multiply both sides by a naught here. So this tells me that the amplitude of this quake was a naught times 10 to the 9.2. You might be thinking, well, how can we possibly figure out what the amplitude was? The way we could do it, we're not actually going to find the amplitude of this quake. What we're going to do is compare this amplitude to the amplitude of the other quakes. So you'll see what I'm talking about when we do it. The Japan quake, again, was a 9.0, and we just plug that into the same formula, and you do the same business. When you do that, you'll find out that the amplitude for Japan, and maybe I should put a little sub j there and a little sub I here, the amplitude for Japan is going to be a naught times 10 to the 9 power. And following the same argument, the amplitude for San Francisco is going to be a naught. San Francisco was 10 to the 8th, I think it was, so times 10 to the 8th power. And now let's go ahead and find out how many times more powerful was the Indonesian quake versus the Japan quake. To do that, you take the ratio of the power output, or the amplitude, of the Indonesian quake to the amplitude of the Japan quake. That'll be a naught times 10 to the 9.2 over a naught times 10 to the 9th. And you'll see the a naughts cancel, so they never really mattered in our problem. You subtract exponents, and you'll get 10 to the 0.2. That, let me grab my calculator here, 10 to the raise to the 0.2 power is about 1.6 times more powerful. More than 1.5 times more powerful. And that's what is a kick in the pants about these Richter numbers. People think that a 9.0 and a 9.2 are very close. They're not. A 9.2 is more than 1.5 times more powerful. And when you're talking a powerful quake, 1.5 times more than that is pretty darn powerful, right? You would never guess that using the Richter numbers. They're just a slow progression of numbers, so you don't really realize the significance of that. So let's go ahead and do the same thing for the San Francisco versus the Indonesian quake. Now remember, I told you the San Francisco quake did a ton of damage, and there was a lot of people who lost their lives during that quake. So here we go. Again, the Indonesian quake has this amplitude. The San Francisco quake has this amplitude. Now we'll go ahead and cancel the a naughts because they will cancel. And you get that this is equal to 10 raised to the 1.2 power. And 10 to the 1.2 power is going to be 15.85. I'll just say 15.8. Roughly 15.8 times more powerful. Now, or times more powerful. Yeah, I guess I could do more powerful. Now that's a huge number of times more powerful. If you had $1,000 and I had 15 times the amount of money that you have, I'd be pretty happy, right? 15 times more powerful than a quake that demolished a city. That's how many times more powerful the quake in Indonesia was. So this is, it doesn't give you all, because remember the Richter number for San Francisco quake was 8 versus the Richter number only being 1.2 times more for the Indonesian quake. So don't be fooled by Richter numbers. They're logarithmic. And so it's very difficult to use them to depend upon any reliable, like, oh, this is this many times more powerful. You know that if it's, the rule of thumb is, if you go up by 1 in the Richter number, the power is up by 10. Okay? If you go up by 2, the power goes up by 100, actually, and so on and so forth. So it's pretty crazy how quickly they go. So anyhow, that's it for this lecture. The next lecture, we're going to focus on logarithmic graphs.